Hey there, so here's the rest of our notes from Thursday looking at section 3.8, our mechanical vibrations. So what we ended up doing in class is we derived the formula for our mechanical vibration looking at all of the forces that you need to add up on this dash pot system. And getting everything on the left-hand side and canceling out a couple of terms here, we derived the formula for our mechanical vibration. And we said, if this is set equal to 0, if there is no external force, then we've got a free vibration and a homogeneous solution. And that's what we did on example 1. We set it up. We had to do some conversions of our pounds to force. We converted all of the inches to feet. We calculated the spring constant here. And then we also calculated the damping coefficient, which is proportional to our velocity here, and setting it up into our formula and adding in our initial conditions. Here is what the setup would look like for this particular system. Then on the second page, we looked at the undamped free vibration. So undamped means you don't have that U prime term in here. There's no gamma. And we saw that the natural frequency of this system, which since there's no damping, it would just be oscillating forever. The natural frequency is found by solving our characteristic polynomial, mr squared plus k equals 0. And we saw that that's always going to produce an imaginary number, this square root of k divided by m times I. And that's where our natural frequency comes in at. So on example 2, we set this one up, again did some conversions. We had, in this case, the natural frequency turned out to be 7. We could have used the little formula and said, well, it's the square root of 98 divided by 2, or just use the characteristic polynomial, your r squared plus 49 equals 0. And that solves out for C. And using the initial conditions, we saw that you get the 1/2 for your cosine and a negative 3/7 for the sine. So where we stopped was right about here, and what we saw on earlier in the week, that this type of an expression or this type of function can actually be written in terms of just a single sine function. And we derived that formula on Monday, but kind of review it a little bit here. We started out with writing our original equation in terms of the constants were a and b here, something like that. And we need to think about this little triangle. So if we write down a triangle and put the a on the vertical and the b on the horizontal, we can see that the hypotenuse is the square root of a squared plus b squared. Also, we can calculate the angle delta, which is our phase shift, as the tangent of delta is a over b. So to begin with, let's go to the left-hand side, and we first need to figure out what the new amplitude of the function is. And so let's take our coefficient a and b. We need to take a squared plus b squared and the square root of that, which is right here. And that turns out to be the square root of 85 divided by 14. So that's our new amplitude r, or on Monday we called it k. And then the next step is just to find out what is that phase shift delta there. So delta, we know, is going to be a divided by b, the tangent of delta. And so here I took delta, take actually the arc tangent, so arc tangent there, of 1/2 divided by negative 3/7, and that turns out to give me negative 0.862. And you might say, okay, that's my phase shift. But if we think about where these points actually lie in the entire plane, we have really a negative 3 in the horizontal, and we've got a positive 1/2 in the vertical. So that really places us into the second quadrant out here, negative 3/7 and 1/2. So the arctangent will only give us angles in quadrant 1 or quadrant 2, or quadrant 4 actually. And we need to get our phase shift in this quadrant too. So we're going to have to add a pi to it. So take our negative 8.62 and add pi, and I get a 2.279. And there is this similar equation, the identical equation, just written differently, from our undamped free vibration. This new frequency here, this 7, is still the natural frequency of our dashpot system. Well, it's not a dashpot system, just the natural frequency of our undamped free vibration. Now, when we do apply a damping to it, that frequency is going to change, and we call that new frequency the quasi-frequency, and then we can find the period of 2 pi divided by that would be the quasi period. So how do we develop the idea of damped free vibration? So let's start out with this damped free vibration equation here. So mu double prime plus gamma u prime plus ku equals 0. And this type of system has multiple different solutions and characteristics. So if we start with, let's just solve it in general, the characteristic polynomial. And there we have mr squared plus gamma r plus k equals 0. We'll have to use the quadratic formula to find the zeros for that. And when we do that, we'll get negative gamma plus or minus the square root of gamma squared minus 4mk, all divided by 2m. Now, we know that from the quadratic formula, we can end up with 2 real roots that are distinct. We can end up with 1 repeated root if the discriminant here is 0. Or if that's negative, we know that we're going to end up with complex roots. Those 3 different situations will all have different characteristics for our system. So the characteristics just depend really on that discriminant. So if we take the discriminant and solve it, we've got gamma squared minus 4mk. Well, let's start out with if it's a positive. So that means we're going to get 2 real distinct roots. But let's go ahead and solve for gamma. So gamma squared would be greater than 4mk. Take the square root of each side, and that's a gamma was greater than 2mk. And from here, let's write down the 3 cases. So this is our first case of gamma is greater than 2 root mk. So if, let's see, if gamma is greater than 2 root mk, we know that with the 2 distinct solutions, real solutions, we'll end up with this as our general solution, and the r's will always be negative, which means this is just going to go to 0, and it'll either go up depending on this your initial conditions, or it might just go down immediately and decay to 0. We call that an overdamped system. It doesn't cross over the x-axis. So think of it like a saloon door that you open up, and when it swings shut, it just slowly closes shut and doesn't do any kind of oscillation swinging there. So that's an overdamped system. Now the second case is if gamma is equal to 2 root mk. We know from here, when we have repeated roots, we'll get this equation, which is c1 e to the rt, and since the roots are repeated, it'll be plus c2 t e to the rt. This is called critically damped, and in this situation, our motion will either start to go up or start to go down, but either way, critically damped could possibly go below that x-axis and come up. Now, there is a critically damped situation where it might not cross that x-axis and just decay, kind of similar to the overdamped, but this characteristic is usually the most common for critically damped. Lastly, if we have gamma is less than 2 root km, we'll get complex solutions, complex roots, and the differential or the general solution will be a combination of the exponential e to the lambda t, where lambda is the real part of our root, times cosine mu t. Mu is the imaginary part, and then we'll have the same thing for our sine term. And this new mu inside the sine and cosine, that's our quasi-frequency. So it changes a little bit. If we remove the damping here, we're back to the natural frequency. But with that damping, we've got a slightly different and sometimes drastically different quasi-frequency. And this type of oscillation it's called underdamped. It's still damped, but underdamped meaning that it will just continue to oscillate until it comes to a rest. And that curve is sandwiched between the envelope of our exponential. So you can draw an exponential curve through here, and it's just kind of narrowing down that oscillation until it eventually will stop. So there's the characteristics of our unforced mechanical vibration. And next week we'll take a look at what happens if we actually supply an external force and make this a non-homogeneous equation. So we'll see you next week.